Welcome to Lesson 4.2. Based on pursuit of the vitamins section of most drugstores, you'd think Americans need a lot of vitamins, and almost 50% of American adults are reported taking some dietary supplement, according to the most recent study published in the 2009-2010 National Health and Nutrition Examination Survey. People take specific vitamin supplements, of course, B, C, D, E, and so on, and if taking one vitamin at a time is too much, one-a-day multivitamins abound, designed for each specific life circumstance. Are you an active man over 50? Support your cell health with extra selenium. To understand how we got to that endless row of vitamins at CVS, it's useful to look at a couple of examples: vitamin D and vitamin E. These are among the most popular vitamin supplements. In the 2009-2010 NHA-NES, 34% of adults reported taking vitamin D supplements and 30% reported taking vitamin E. One can find plenty of support for this supplementation behavior in the medical literature. A recent review identified 290 observational studies on vitamin D. For the most part, these studies measured the amount of 25-hydroxy vitamin D, the marker of the vitamin D concentration, in participants' blood, and analyzed the relationship between the concentration of various amounts of health. Using this approach, researchers have found that higher concentration of vitamin D are linked to less cardiovascular disease, lower overall mortality, less weight gain, less diabetes, less likelihood of getting infectious disease, less multiple sclerosis, fewer mood disorders, better cognitive function, basically every outcome under the sun. Based on these studies, vitamin D is pretty much a philosopher's stone. Based on this excerpt, we can conclude that taking vitamin D, or can we conclude that taking vitamin D causes all of these great health benefits? The explanatory variable is your vitamin D concentration. The results of this study of 290 observational studies of vitamin D is that each subject either had a high vitamin D concentration or a low vitamin D concentration. If they had a high vitamin D concentration, they might take the vitamin D supplement. They might also be active outside because vitamin D is absorbed from the sunlight. They might also therefore exercise a lot. If they're outside, they might just be active people. They might be outside running. In the winter, they might be outside skiing. Okay, they might have a balanced diet because if they take vitamin D, they might also be health conscious. Or if they have a lot of vitamin D and they're outside, they probably do other things that are healthy. And they had a lot of good health outcomes. People with low vitamin D concentration, first, don't take supplements of vitamin D, and second, they aren't outside to absorb vitamin D from the sunlight. So they're not taking the supplement, they're not outside, so they're probably not exercising, or they're at least not living an active lifestyle and hiking and seeing the outdoors and going on walks and playing with their dog. They might also therefore not eat healthy if they don't do these other things. And they had bad health outcomes. Okay, the confounding variables are these. There are other variables affecting the response in the same direction as the explanatory variable. So these other variables alone also provide good health outcomes, and these other variables also provide bad health outcomes. But they're associated with people that have high vitamin D concentration, and these types of activities and lifestyles are associated with people with low vitamin D concentration. The response variable is this amount of heart disease and etc. that people have, and diabetes and high weight and heart disease and all these other things. Explain the concept of confounding in this context of the study. So, is it vitamin D alone that gives us low mortality, low weight gain, less diabetes, less likelihood of getting an infectious disease, and all these other things? No, vitamin D doesn't directly account for all of that. Vitamin D only directly biologically has a certain process inside the body. But people with high vitamin D concentration tend to have these types of lifestyles, and therefore they tend to have good health outcomes. People with low vitamin D concentration either don't take vitamin D supplements or they're not outside, and therefore they have all these unhealthy outcomes. So This, these things, though, are outside of the vitamin D pill. Being outside, exercise, balanced diet, caring about your body. Okay? These people that might not care about their body are not outside and are not doing good and trying to think positive and do well for themselves, that have bad health outcomes. All those other things are confounding variables. So we can't just look at vitamin D concentration and know that the pill is making this happen, or the pill alone is the lack of the pills making that happen. It's hard to do an observational study and to just find these people and find concentrations in their body and know exactly what the cause is for these health outcomes or those bad health outcomes. Okay, so that's confounding variables. There are other variables that are associated with the variable of interest that aren't controlled for and that result in getting the same outcome. Okay. And, okay. All right, that's good there. All right, two variables are confounding if it's impossible to determine whether the variable causing a change in the response, which variable is responsible for causing the change in the response variable. Here, while people taking vitamins have good health outcomes, people who take vitamins might also make other choices in diet and exercise, which are also known to result in better health. Okay, potato consumption is commonly associated with poor health, and diet fads put potatoes on the no-no list. Perhaps potatoes themselves are confounded with negative weight gain because of how they tend to be prepared, especially by the population that is overweight. And what are they served with? Cheesy fries, anyone? So potatoes are placed on the no-no list by diets, not because potatoes are bad for you, but because people think, oh, potatoes are good for me, so they stuff more french fries in their face, they eat more potato chips, they take the loaded fries, they go with that, I don't know, curly fries, just anything potato related, including that stuffed potato at the salad bar where you put all the sour cream and bacon and cheddar on it. It's just no longer a good deal. And then melted butter all over it. Okay, potatoes tend to be prepared bad, so that's why they're on the no-no list. So that's another example of something that has confounding variables. The potato is not bad, it's everything else that's bad. Okay, what are some differences between an observational study and an experiment? In an observational study, we observe individuals and measure variables of interest, but we do not impose treatments and we do not attempt to influence a response. In experiments, we deliberately impose treatments on individuals to measure their response. Okay, so before, when we looked at the vitamin D thing, that was a study of an observational study. That was where we just took people, assessed whether they had vitamin D, and then looked at their health outcomes. Now, if we were to turn that into an experiment, we would actually take people and then ask one group to take vitamin D, ask another group to not take vitamin D, and then watch and see if there's a measurable effect on their health at the end of the study. What's the difference between an explanatory variable and a response variable? An explanatory variable is manipulated by the experimenter to determine its relationship to an observed phenomenon. A response variable is the effect, the outcome of the study. Okay, so an explanatory variable could be the vitamin D. We can give people a low dose of vitamin D, a high dose of vitamin D, and the third group no vitamin D. And then the response variable might be heart disease. And we see if the people with no vitamin D or low vitamin D or high vitamin D, how they compare in their development of heart disease. Or we could use diabetes. We can see if any of them develop or cure of diabetes. We could check for mood disorders and see if any of them develop or cure of mood disorders or anything else. Okay, check your understanding. In groups, discuss explanatory and response variables in each study. Does reducing screen brightness increase battery life in laptop computers? To find out, researchers obtained 30 new laptops of the same brand. They chose 15 of the computers at random and adjusted their screens to the brightest setting. The other 15 laptop screens were left at the default setting, moderate brightness. Researchers then measured how long each machine's battery lasted. Was this an observational study or an experiment? And justify your answer. Well, did we not impose treatments and not attempt to influence the response, or did we deliberately impose treatments? I think we deliberately imposed treatments. We specifically went in and cranked up 15 laptops to the brightest setting and another 15 laptops left at a moderate setting. So we controlled that. So the explanatory variable is the 15 computers and their adjusted screen brightness. The response variable was the length of the battery life. Okay. And then it was an experiment, not an observational study, because the variables were controlled for, except screen brightness, and random assignment took place. Okay. All right. Question 2 refers to the following setting. Does eating dinner with their families improve students' academic performance? According to an ABC News article, teenagers who eat with their families at least 5 times a week are more likely to get better grades in school. The finding was based on a sample survey conducted by researchers at Columbia University. Was this an observational study or an experiment? And justify your answer. We would say this is an observational study because they didn't manipulate eating with families. They just let it happen first, then they measured a response. So instead, if we took people and if we made them sit with their families at dinner and made them not sit with their families for dinner, for a formal sit-down dinner, and then measured a response, then we can see if then we could be doing an experiment. But in this case, this was just an observational study because we just let it happen. We just went and found people and saw if they ate with their families and then looked at their grades. What are the explanatory and response variables? Okay. The explanatory variable was eating dinner with your family. The response variable was your grades. Explain clearly why such a study cannot establish a cause and effect relationship. Many other variables affect grades, such as work, sports, your interest in school, the belief in one's future, study skills, capacity, like are you smart or aren't you? Maybe kids who eat dinner at home greater than 5 days a week also don't hold a job and therefore have more time to study. Okay, so those are other variables that affect your grades. If you're sitting at home eating, it's not actually the sit-down time with your family that influences you to do better at school, maybe. Maybe it's the fact that you have the time, okay? That also means that you have more time in your life in general, so you can better get your homework done. We cannot establish cause and effect unless we can control for confounding variables. Random assignment is linked to cause and effect. So what we need to do is we need to control for other variables, and that's where the control aspect comes in. If I was to assign a random group of people to eat with their family and assign a separate random group of people to not eat with their family, then it seems like I'm controlling that they're eating or not eating with their family. But really in experiments, control means that I'm trying to keep the groups as similar as possible within, except for that one factor. So I'm actually controlling for the fact that I'm putting smart and low achievers together. I'm putting workers and non-workers together in a group, and I'm putting athletes and non-athletes together in a group. And then I'm telling them, don't eat with your family. And then I'm making the same mixed up group of all those background tendencies, I don't know, and workers, non-workers, athletes, non-athletes, high achievers and low achievers in a group, and I'm telling them to eat with their family, and then I'm seeing what happens. And that's what I mean by control. I'm controlling that the two groups are as similar as possible. Okay, briefly define the following terms. Treatment, a specific condition applied to the individuals in the experiment. If an experiment has several explanatory variables, a treatment is a combination of specific values of these variables. The experimental units is the smallest collection of individuals to which the treatments are applied. The subjects, The experimental units that are people, because we just try to find a different word for people. Factor. In the hypothetical experiment above, there are two factors, dosage of vitamin C and dosage of vitamin E. Level. Of the factors vitamin C and vitamin E, vitamin C has 3 levels, vitamin E has 2 levels. Okay. All right. If you are asked to identify a possible confounding variable in a given setting, you are expected to explain how the variable you choose is associated with the explanatory variable and how it affects the response variable. Designing experiments. Suppose we wanted to design an experiment to see if caffeine affects pulse rate. Here's an initial plan. Measure the initial pulse rate, give each student some caffeine, wait for a specified time, measure the final pulse rate, compare final and initial rates. What are some problems with this plan? What other variables are most likely to be sources of variability in pulse rate? Other activity from the initial to the final pulse check. Imagine that we also let the people walk around or dance around, or that they're freshmen, they're going to jump around and play around and roll around. The environment, the temperature, the stress. Are we then moving them all to a hot room or a really cold room? Are we actually making them worried about their general health and that their stress is going to increase their pulse rate? Is there sugar in the drink? That would be a confounding variable. Maybe it's the sugar that's making their pulse go up and they're actually not affected by caffeine. Who? I don't know. There are several steps we should take to solve these problems. 1, the first step is to include a control group that does not receive any caffeine. What is the purpose of a control group? To provide a baseline for comparison. Otherwise, any pulse rising or lowering event that occurs during the experiment would be confounded with the caffeine. For example, an amazing stats lecture during the waiting period would certainly raise pulse rates, making it hard to know making it hard to know how much of the pulse increase was due to the caffeine. What should the no caffeine group get? Nothing? Sprite? Caffeine-free Coke? The second step is to make sure the two groups, caffeine and non-caffeine, are as similar as possible and are treated in exactly the same way, with the exception of the treatments. To make this happen, we use random assignment, replication, and control. What is the purpose of random assignment? To create groups that are roughly equivalent at the beginning of the experiment. Random assignment ensures that the two groups are as alike as possible at the beginning. We must always randomize, since there will always be other variables we cannot control or that we do not consider. Randomizing guards against what we don't know and prevents people from asking, but what about this variable? So that's where we suggest that randomization provides control. True, we aren't actually controlling for all the other variables. But if we make randomized groups, we will know that our two groups are hopefully as similar as possible and that they both have all the same other variables that could affect the outcome of the study. How do we randomize? What is a completely randomized design? It's a design in which the experimental units are assigned to the treatments completely by chance. Remember, not by us, but completely by an outside device. What is replication? Replication is ensuring that there is an adequate number of units in each treatment group so that the two groups are as equivalent as possible. Then, differences in the effects of the treatments can be distinguished from chance differences between the groups. Note, replication can also refer to the repeating of the experiment with different subjects. This can help us feel more confident applying the results of our experiment to larger population. Many times in the real world, experiments are repeated and they're published online in a forum or in a journal, and other people then are able to go and see if they can replicate the experiment. And sometimes when experiments can't be replicated, that needs to be posted to say that, hey, this experiment was replicated and I can't get the same results that the first experimenter did. And then that kind of cuts a hole in the first experimenter's experiment. Okay, what does it mean to control for other variables? It means holding other variables constant for each member of both treatment groups. So therefore, if we let the people roll around on the floor, then we have to let both groups roll around on the floor. If one group's going to get an AP Stats lecture during the wait time, then the other group is going to get that same lecture. Okay? Preventing confounding. If one treatment group was given regular Coke, which has sugar, and the other treatment group was given caffeine-free Diet Coke, which has no sugar, then sugar and caffeine would be confounded. The Coke group had caffeine and sugar. The Diet Coke group got neither. So if we saw a difference in the heart rate of the Coke and Diet Coke, was it due to caffeine alone, or was it due to caffeine and sugar, or just sugar? Okay, to prevent sugar from becoming confounded with caffeine, we need to make sure that members of both treatment groups get the same amount of sugar. Reducing variability in the response variable. If we let subjects in both groups drink any amount of soda they want, the changes in pulse rates will be more variable than if we make sure each subject drank the same amount of soda. In the second set of dot plots below, the additional variability in pulse rate changes makes the evidence for caffeine less convincing. So here we look at the caffeine group and the non-caffeine group, and then here we look at the caffeine group and the non-caffeine group when they were able to drink any amount of soda they wanted. So if they were able to drink very little soda or a whole lot of soda, their pulses varied more than if they had to drink the same amount of soda as one another. Same idea happened here. The non-caffeine group all had an average of no change maybe in pulse rate, but here they're more spread out, and in general, in AP Stats, we don't really like spread. We prefer that our sample was closer together because then it would give a more precise estimate of that true parameter value, like around 6 for the change in pulse. Will weight be a confounding variable in this experiment? Yes, weight will be a confounding variable, but if we mix up weight in both groups in the random assignment process, then we should have light weights and heavy weights in both groups, and then it should work out in the end when we take an average pulse of each group and then get the change in pulse. Okay, what is a single blind experiment? When neither the subjects or researchers are unaware of who is receiving the treatment and who is receiving the placebo. Single blind means that one group is blind to this. Now, when would that happen? That would happen when maybe, let's say more likely, the researchers are aware of who's getting the treatment and the placebo, but the people are not. So let's say that I go in for a flu shot, and let's say that I'm in an experimental study to see if the flu shot is working. Well, then I might just be getting a shot of nothing, or I might be getting a shot of the flu shot. Okay, now maybe the researcher knows which I'm getting. So maybe especially the doctor right there that's giving me the shot knows which one I'm getting. Maybe the one tube has a little green sticker on it, and that means treatment. Maybe the other tube has a red sticker on it, and that means placebo. So maybe that would make the physician act a little differently and act a little more excited, like, ooh, good, I know this person's going to be protected. Or make the doctor a little more bummed out. Oh, darn it, this person's going to be sick. I feel so conflicted that I'm giving them just a placebo. That might affect the way that doctor visit goes, okay? And it might make the patient feel a little weird too, okay, based on how that doctor made the patient feel because of the patient's excitement or letdown. What is a double-blind experiment? This is when both the subjects and the researchers are unaware of who is getting the treatment and who is getting the placebo. It is possible when the statistician knows the difference between the identities of the treatment groups. But in the meantime, the doctor won't know the difference. So the doctor, either way, is just like, hey, good luck, dude. Okay, and you're getting a placebo or you're getting a treatment, and I got no clue. Okay, and so the doctor will be equally upbeat for everybody. Why is blindness important? Use blindness so that the patients all believe equally in the effects of their treatments, and so the physician also believes. Blindness is important because if the patient feels that they're just getting nothing, then they're going to have an internal belief in that nothingness, and they're going to feel a little bit more down about their chances of survival and maybe a little more frustrated. And all that downness and frustration is actually going to affect the body and make the body handle the situation a little bit worse. But instead, if the patient knows that they're in the treatment group and that they're getting the real flu shot, then they are going to be a little bit more excited and optimistic, and they're going to have an internal belief in their ability to get over the flu. Okay, so it's important instead that everybody has that forward-paced, good momentum, positive thinking, I'm going to fight this off kind of placebo effect. Okay, that they're going to fight that disease and that they're going to do good. Okay, what is the placebo effect? It describes the fact that some subjects respond favorably to any treatment, even in an active one, like a placebo. So the placebo effect is saying that if you get that placebo, you might still believe, hey, I'm doing this. I'm out there, I'm being researched on, I'm going to fight this flu the best I can. And that might actually make the body fight the flu better than somebody who doesn't even get a placebo. So, not all experiments have a control group or use a placebo, as long as there is a comparison. So, if you are testing a new drug, it is usually compared with the currently used drug, not a placebo like a sugar pill. Also, you can do an experiment to compare 4 brands of paint without using a placebo. So just some pointers here. In case we're curious if a headache pill works, I might not give my patients a headache pill and a sugar pill, which might do nothing. I might instead give them my headache pill that I'm trying to research and aspirin, okay? Which I know works because I would feel bad about giving them nothing and really letting them sit there with that bad headache, okay? So I would still maybe give them something, but I would test to see if my new research pill is going to do better in curing the headache than the old one did, okay? Also, you don't really need a placebo if you're going to test paint on the roadway. Say you have a busy, windy road and you're trying to test the paint on it because you know that tires go off the painted lane kind of frequently on that road. So, would it be wise to not paint a section and then to paint the next 4 sections with your 4 different types of paints? Probably not wise to not paint a section, okay? We don't need that level of a control group where there's no paint to compare to. If we just compared all 4 paint brands with each other, then that would be great. If I had a non-painted roadway on a curvy road, I would get a lot of accidents at nighttime. So try to think of what is a reasonable placebo or control group for each of the different real-world situations you read about. Okay. With random assignment, replication, and control of other variables, each treatment group should be nearly identical, and the effects of other variables should be about the same in each group. Okay, so it's important that we're not eliminating other variables, but we're trying to balance out the effects of the other variables and make sure that they're balanced as best we can by chance between the 2 groups. Now, if changes in the explanatory variable are associated with changes in the response variable, we can then attribute the changes to the explanatory variable or the chance variation at the random assignment process. Okay? So now one of 2 things exists. if we see a change between our new headache pill and our aspirin, one of two things happened. Either by chance, the people put in the new headache group were just going to get better, okay, then the aspirin group was going to get better, or truly the new headache pill did work better than aspirin did, okay? So possibly, even though we used a random assignment process, it wasn't up to us to put the people in the new headache pill group and in the aspirin group. Possibly all my better curing people that were just destined to get better were over here and not over here. Or possibly this pill really is better than that pill. Which is it? We don't know that distinction, okay? But all we can do in this class is look at the numbers and say if that distinction really did exist. And if we think that that's beyond a reasonable doubt, that even a bigger growth happened in the curing of their headache over here than tends to happen by chance assignment on its own. Okay. Now, in an interesting experiment, researchers examined the effects of ultrasound on birth weight. Pregnant women participating in the study were randomly assigned to one of two groups. The first group of women received an ultrasound, the second group did not. When the subjects' babies were born, their birth weights were recorded. The women who received the ultrasound had heavier babies. Okay, a couple things about ultrasound. Women don't really get it that often during a pregnancy unless doctors think that it really, really is necessary. So for a healthy pregnancy, a woman gets one ultrasound, okay? Now then, if something's going wrong, they'll do more, okay? And also another fact, you do want a heavier baby. Heavier babies feed better, they survive better, they just have a whole bunch of survival characteristics about them that are stronger than lightweight little babies. Okay, did the experimental design take the placebo effect into account? And why is this important? No, the women in one group didn't get anything in the place of ultrasound that the other group received. So we read that one group got ultrasound and the other women didn't. The placebo is important to show whether the birth weight is attributed to the ultrasound effect, to the ultrasound itself, or to the placebo effect. The placebo effect is that the mom sees her baby, so she eats better, tries harder to be healthy for the baby. Okay, the mother's experience, the placebo effect is the mother's positive experience from having the ultrasound. And there it's explained. So, was the experiment double-blind, and why is this important? No, the doctors definitely knew that they were giving the ultrasound, and the women definitely knew that they were getting ultrasound. Okay, no, each mom knew that he or she got or didn't get the ultrasound. Okay. So why is this important? If the mother knew that she didn't get ultrasound, then she might feel a bit bummed out that she didn't get the opportunity to see her baby. Okay. And if the doctors knew that the mother didn't get ultrasound, then the doctors might feel a little bit, unsteady about the health of the baby too, because they didn't get measurements on brain, lungs, kidney function, and does the baby have two legs, and all that stuff, and are there different chambers of the heart? Okay, the doctor can't see any of that and can't know how to advise the mom. Okay, based on your answers to question 1 and 2, describe an improved design for this experiment. Treat all mothers the same. Give a false ultrasound to one group of mothers. Make sure the experience is identical for this false ultrasound group as the experience for the group that does get ultrasound. Perform a single blind experiment where ultrasound tech doesn't let the mothers know which treatment group the mother is in. Here, the ultrasound tech would have to know that she's giving a fake ultrasound because she's trying to move the little ultrasound thing to see the baby's noggin, to see inside the brain and to see the different hemispheres of the brain there, left side, right side. And then she's trying to move it to see the lungs. And if there's not a real ultrasound going on, then she's going to know she's going for lungs, but that the video of the ultrasound is going for feet. And she's like, no, I'm trying to get over here to lungs. And the video keeps showing feet for a little while. And she's like, no, come over here. And not showing that part. So she's, huh? Okay. So it can't be double blind. Okay. But it can be single blind. And she can perform a fake ultrasound with just a little video of another mother's ultrasound going on. Okay. On the video screen, another like images of the baby. Okay. And she can just try to make it seem as natural as possible. Okay. The results of an experiment are called statistically significant if they are unlikely to occur by random chance. That is, if it is unlikely that the results are due to the possible imbalances created by random assignment. The caffeine experiment. If caffeine really has no effect on pulse rates, then the average change in pulse rate of the two groups should be exactly the same. However, because the results will vary depending on which subjects are assigned to which group, the average change in the two groups will probably differ slightly. Thus, whenever we do an experiment and find a difference between two groups, we need to determine if this difference could be attributed to the chance variation in the random assignment or because there really is a difference in the effect of the treatments. Increases in heart rate in 14 students are shown below. Note that the negative values mean their heart decreased. So here's the people that drank the caffeinated soda. They had an 8, 12, 10, 14, 2, 0, 0 beats per minute increase or no increase in heart rate. And the non-caffeinated soda. Some of these people's heart rate went down, some went up a little, okay? And we needed that non-caffeinated soda just so that we can see the variety and the average change that happens in this group that gets everything else the same during the waiting period, from drinking to the final measurement of the heartbeats and then subtracting the before and after heart rates. How can we tell if the results in our experiment are statistically significant? Is 6.57 beats per minute really actually a significant result? Or is that so few beats per minute that it doesn't actually prove a difference? So is the caffeine mean minus the control mean, the non-caffeine mean, that's equal to 7.71. Is this a statistically significant difference in heartbeat per minute? Okay, so write each person's increase in heart rate on an identically sized wooden pog. Assume the caffeine has no effect on heart rate. Shake the pogs and deal into two piles of 7. Pile 1, caffeine group. Pile 2, non-caffeine group. This is a simulation that will help us try to see that if we got all these differences in caffeine, and if they were randomly assigned, and it had nothing to do with the caffeine itself, if they were randomly either in a caffeinated or non-caffeinated soda group, how often do we get a difference in caffeinated versus non-caffeinated, like 7.71 just by chance? So, calculate each group's mean using technology, find the simulated difference, caffeine versus non-caffeine. Repeat the process 2 more times and make a class dot plot. Answer the question, how often did the difference of 7.71 or more occur? Based on the results of the experiment, what is the evidence that one of the drinks increases pulse rates more than the other? So here was my class that did this last year, and we should have really done this over here in this nice space and over here in this table. Okay, but here's my class's sample differences. So what they did is they shook up their pogs, they put each of these numbers on a pog for each person's difference in pulse rate from before and after drinking caffeine or non-caffeinated. And then they shook them up, spat them out, and subtracted the mean differences. And this is the mean difference, 7.71, that we got above. So we believe this difference, 7.71, is not due to chance variation in the random assignment process, but instead due to the caffeine. There is a statistically significant 1 in 30 odds of this happening by chance alone. Okay, it only happened 1 out of all 30 times that the sample mean difference between caffeinated and non-caffeinated was greater than 7.71. Okay, this assumption, caffeine has no effect on heart rate. The assumption, caffeine has no effect on heart rate. The difference observed above is due to random assignment. Can we disprove this? Okay. All right. What are the two explanations for this evidence? There is no difference between the two drinks, and we got a difference due to the imbalances in random assignment, or there is a difference in the effectiveness of the two drinks, and we thought that we got that answer. Okay, blocking. Many students enroll in prep courses to improve their SAT scores. 20 students who have taken the SAT once volunteered to participate in an experiment comparing online and classroom prep courses. Describe how we can use a completely randomized design to compare online and classroom SAT prep courses. Number the students 1 through 20. Randint 1, 20 to generate 10 unique numbers, skip repeats. The 10 students whose numbers were selected will take the online SAT prep. The other 10 not selected will take the classroom prep. Okay, it's bad to do this instead, to flip coins as students arrive. Heads, send them to the online group. Tails, send them to the classroom group. Say our first 15 students to arrive, you already have 10 in the online group. Do you put the last 5 in the classroom group? This could lead to bias. They could be the least motivated people, are the last ones to arrive. So make sure that you never are like putting a chunk of people that all have something in common into one classroom because of your chance device that you're using is leaving you with a chunk at the end. So instead, it's better to try to number 1 through 20 and generate 10 unique numbers, skip repeats. These 10 students who were selected will all go into the online SAT prep, and the others selected will take the classroom prep. It's okay in that way to just select 10 and then to put all the rest of the 10 in the classroom prep, because they're coming from an alphabetical list, and alphabet has nothing hopefully to do with academic ability and academic drive. And when you generate 10 randomly from a list that's alphabetized, then the leftover 10 especially have nothing to do with each other and don't have any characteristic like motivation in common. Okay, among 20 volunteers, 10 are in pre-calc, 6 are in algebra 2, 4 are in geometry. What problem does this cause? Chance variation in the random assignment process might put all the pre-calc together in one treatment group. This would lead to an overestimate of that teaching method's effectiveness. It adds extra variability to have all these different ability levels in juniors taking an SAT prep course, or maybe they're seniors. Okay, so let's scoot this over. How can we address this problem? 1, eliminate the Algebra 2 kids and the Geometry kids from the study. Consequences, your results then only apply to your pre-calc kids, and you can't apply those results to all types of kids. So then let's keep them and let's block. To group or block the kids by math class, then randomly assign within the blocks. Okay, so here are the results of the experiment using math level as a blocking variable. Make dot plots to compare the improvements of the students in the online course to the improvements of students in the classroom course. Based on the dot plots, does there appear to be any convincing evidence that the online course is better? So these pre-calc kids took it online and their improvement was this many points. These pre-calc kids took it in the classroom and their improvement is this many points. So by just eyeballing, we think that maybe the pre-calc kids did better had bigger improvement online than they did in the classroom. Okay, but all kids did improve. Then we had Algebra 2 kids that took the class online and in the classroom, and we see 50, 60, 40 were the improvements, and the improvements in the classroom are 30, 40, 20. So it seems like the average improvement online was bigger than it is in the classroom. And geometry online seemed to be better as well than geometry in the classroom. Okay, as both these numbers are bigger than 0 and 20 for the improvements. Now, here's a dot plot that places those improvements then. And if you just look for any dots, it seems like the classroom improvements were generally lower than the online improvements, which were generally higher because the minimum online improvement was about 30 and the minimum classroom improvement was 0. And the maximum online improvement was 100, where the maximum classroom improvement was 80 points. So the maxes and mins are higher than these maxes and mins, and it seems like the middle will also be higher than the middle of this. All right, the dot plot in number 3 ignored the fact that we blocked by math level. Here's a dot plot again using the different symbols for the students in each math level. Okay, so I guess I didn't have some number 3. All right, but over here now I put different symbols in for the math class that they were in. All right, and over here then I took a number and I subtracted to try to level out all of the students' scores, and I talk about that here. Notice that within each math level, the online students clearly did better. We couldn't see this difference when we ignored the blocks. The average improvement for students in pre-calc was 86, the average improvements for students in Algebra 2 was 40, and the average improvements for students in geometry was 20. How can we use this information to account for the variability created by differences in class level? We can level the playing field. We can subtract 66 points from each pre-calc student, subtract 20 points from each Algebra 2 student, then we will have better way to compare where the advantage of being in pre-calc or the advantage of being in Algebra 2 is taken out. And then we get this type of point distribution where the people are much closer together. Except one online student, all online students had greater improvement in SAT than the classroom students. This shows that for geometry, Algebra 2, and pre-calc students, that the online program is better at improving scores. Okay. Blocking in experiments is similar to stratification in sampling. Blocking accounts for a source of variability, just like stratifying. This means that blocking is a good way to increase power. We'll get to that word much later. Blocking is a good way to increase your chances of finding convincing evidence of your statement's hunch. Blocking increases the likelihood of finding statistically significant evidence. It makes estimates of variables more precise. Blocking should be chosen like strata. The units within the block should be similar, but different than the units in the other blocks. You should only block when you expect that the blocking variable is associated with the response variable. Blocks, like strata, are not formed at random. In general, how can you determine which variables might be best for blocking? Use the variables that are most strongly associated with best predict the response variable. The units within the block should respond similarly, but differently than the units in other blocks. What is the difference between blocking and stratifying? Blocking is in experiments. We're going to block the treatments groups and block the experimental subjects or whatever it is that the people are, or the animals or things, as stratifying is to sampling, like questioning. A popcorn lover wants to know if it's better to use the popcorn button on her microwave oven or to use the amount of time recommended on the bag of popcorn. To measure how well each method works, she will count the number of unpopped kernels remaining after popping. She goes to the store and buys 10 bags of each of 4 different varieties of microwave popcorn: movie butter, light butter, natural, and kettle corn, for a total of 40 bags. Explain why a randomized block design might be preferable to a completely randomized design for this experiment. The answer: the variety of popcorn will likely be a source of variability in the response variable, number of unpopped kernels. Blocking will help account for this variability. Outline a randomized block design for the experiment. Block by popcorn flavor. Number the bags of popcorn in movie butter 1 through 10. Randomly select 5 bags using randint 1 to 10, skipping repeats. Pop them with an automatic popcorn button. The other 5 movie butter bags get popped according to the instructions. Count the unpopped kernels. Compare the results. Repeat the same process for the other popcorn types. Compare results of the other flavors separately. Combine results for each type after accounting for differences in average responses. A common type of randomized block design for comparing two treatments is matched pairs design. The idea is to create blocks of matched pairs of similar experimental units, like two similar people. The same person with different parts of their body, like the right arm and the left arm. I'm going to put a tattoo on both of your arms, okay? The same person, but a different day. I'm going to do a mindfulness activity today, and I'm going to do a mindfulness activity tomorrow. Okay, using studies wisely. Okay, the scope of inference refers to the type. Oh, hey, we made it all the way. That is lesson 4.3. Sorry about that. All right, guys, great job. That is a lot of information. I'll just go a little bit more into matched pairs for a sec. Matched pairs design is a subset of blocking. It's a type of blocking where you are going to take and try to make two treatment groups, let's say, and you try to make them as similar as possible. So let's say you're going to talk about satisfaction of a relationship. Then you're going to try to take each couple as they walk in the room and try to ask them questions about their satisfaction in their relationship together. So you're going to take the little smiling wife and the little smiling husband holding hands, yay, okay, and you're going to flip a coin and you're going to say, okay, wifey, you go to group 1, and husband, you go to group 2. Then you take the next couple that walks in, yay, okay. Flip a coin. Oh, now wifey, you go to group 2, husband, you go to group 1, and you keep flipping and you keep splitting them up, okay? And they're randomly flipping and going to either group. So now you have a group of all husbands and wives and another group of all husbands and wives, and they're as similar as possible because they came from the same partnerships, okay? And you're going to ask them questions about their satisfaction in their marriage, okay? And maybe you're going to have a really happy person asking these questions and a really grumbly person asking these questions, and you're going to test for a difference between satisfaction in their marriages. I don't know, whatever your test items are, okay? But matched pairs design works like that. Two similar people are being separated, or the same person with both arms getting a little rub-on, wet tattoo, like a little kid. Or same person, different day, or something like this, okay? So matched pairs is a really great way to do a design if it's possible to get twins and separate them into the two different treatment groups, because then your treatment groups are as like each other as possible. Okay, that's about it. Okay, thanks guys.